Hi boys and girls, this is lecture 1.5 in Unit 1. The topic is exponents and polynomials. We're going to start with a brief review of properties of exponents. Remember that a to the 0 is 1, anything to the 0 power is 1, and then a to the negative n, this negative exponent simply means that a to the n quantity belongs in the denominator of the fraction or in the other part of the fraction. A negative exponent in the denominator would mean that quantity belongs in the numerator. If you have two expressions with the same base being multiplied, you can add the exponents. If you have two expressions with the same base being divided, then you can subtract the exponents. If you have an expression raised to a power and then another power, then you can multiply those two exponents. And if you have a product that's being raised to a power, then each factor of the product can be raised to that exponent. Similarly, with a fraction, the exponent can be applied to both the numerator and denominator of that fraction. And then if you have a fraction raised to a negative exponent, then the negative exponent flips the fraction and the exponent can be applied to the reciprocal of the original fraction. Now let's simplify a couple of these expressions and see how to use the properties of exponents. First of all, let's remember that z to the 0 or anything to the 0 is 1. So essentially all of this is being multiplied by 1 and it's not really going to factor into our solution. Also remember that if there are numbers out there, coefficients, that those should be reduced as a normal fraction would be. 4 over 24 reduces to 1/6. Now what I like to do in simplifying these is move everything to its happy place. If a quantity has a negative exponent, I think of it as unhappy, and if a quantity has a positive exponent, it's happy. So all of the happy things will leave where they are, the y squared and the x squared, but the unhappy things, this y would clearly rather be in the numerator, and this x would clearly rather be in the denominator. Now that we have everything in their happy place, we can simplify. This is y cubed in the numerator, 6x cubed in the denominator. Now for the next example, notice we have this lurking exponent. We learned over here that if there's a product being raised to an exponent, that exponent can apply to each of the factors. So this will be distributed to each of the factors inside the parentheses. That means we're going to have 2 to the negative 2, and then negative 1 times negative 2 gives us a squared. 3 times negative 2 gives us b to the negative 6th power. The denominator hasn't changed. And now it's time to move everything to its happy place. You can see that the 2 squared would prefer to be in the denominator. This a squared is just fine, but these 6 b's would rather be down here. These 2 a's were happy, but these 4 b's would rather be in the numerator. The a squareds cancel, and these 4 b's cancel with the 6, leaving just 2. Nothing left in the numerator means we need to put a 1 there. This will be then 1 over 4b squared. Now we're going to graph polynomial functions and look at this happy little graphing calculator. We're going to graph them fully using the functionality of our graphing calculator. To graph a polynomial function, use a table of values to plot points to determine the shape of the graph's middle portion, locating and labeling extrema along the way. If this is your polynomial function, there's going to be a section where some action is happening. You'll have some local mins, maxes, etc., and then there will be end behavior, what's happening at the ends of the functions. Then use what you know about end behavior to sketch the ends of the graph. The end behavior of a function's graph is the behavior of the graph as it approaches positive or negative infinity, this way or that way. Then the end behavior is determined by the degree of the function and the sign of its leading coefficient. If the degree of the polynomial is odd, in both cases, notice end behavior is different. It either starts down and ends up, or it starts up and ends down. If the leading coefficient is positive, you'll have a down-up end behavior scenario. If the leading coefficient is negative, you'll have an up-down end behavior scenario. Now notice if the degree is even, then end behavior is the same. It's either going to start up and end up or start down and end down. Positive coefficient means up, up. Negative coefficient means down, down. Now, this notation down here is initially kind of confusing, but it's just saying f of x, the y value is approaching negative infinity as x is approaching negative infinity. So as you're going this way on the x-axis, you're going this way on the y-axis. Let's look at an opposite scenario. F of x, the y value is approaching positive infinity as x is approaching negative infinity. So as you're going this way on the x-axis, you're going to positive infinity on the y-axis. So that's what that notation means. So let's practice graphing a polynomial function, and to help us out, I have brought my old friend, the TI-84 graphing calculator, to help us. I'm just going to demonstrate what you would need to do in order to graph your polynomial function. First of all, you would click on the y equals menu, which is where you enter your function, and then we're going to have x to the 4th power. I'm just entering the function to the left. Then it's going to be minus x to the 3rd minus 4x squared plus 4. Once you have it entered correctly, then you hit the graph key and you see the function. Now notice that here is the function. It's a little bit larger here. We need to examine to see where is the action happening, because depending on where that's happening, that tells us what x values to put into our table of values. I would say maybe from -2 to +3 we see some action happening. So let's enter -2, -1, 0, 1, 2, 3 in the x part of our table of values. Now let's look at the y values on our graphing calculator. I need -2, so let me scroll up one. -2 is 12. -1 is 2, so nice to just write them down from our calculator. 1, 0, 2, -4, and 3, 22. Okay, now that I have these values, I'm going to put this away for a moment and actually plot the points. I'm going to go -2, 12. I have -1, 2. 0 is 4. 1 is 0. 2 is -4. And 3 is 22, which takes us up to here. Now I'm definitely, gonna try to graph this and we'll see how it goes. Something like this. Now yours is much better, I'm sure, but at this point we should definitely inspect our graph and compare it to this one. Now this looks slightly different because, as you can see, I have the y-axis covering a lot more values than the x-axis, so it's a wider looking graph. But essentially the shape is correct. I'm interested in a few things. I'm definitely interested in this minimum value, this maximum value, this minimum value. Let's use our calculator to find out exactly what they are. In the Calc menu, which we can access by hitting Second, Trace, we have a function called min, and I'm going to enter that. And it's going to ask me for the left boundary of the minimum I'm interested in, so I'm scrolling over to the left of the point I'm interested in, enter. It then asks me for the right boundary, so I scroll over to the right till I'm just to the right of it. I just need to give it a range. Notice the little arrows are designating where they're looking for the minimum value. Then it asks if you want the calculator to guess, and you say, of course I want you to guess, and there we have it. That minimum value is -1.09-ish. Let me go ahead and label that. -1.09, whoops, comma, and then 1.95. Great, we found a minimum value using our calculator. Now let's go back to the Calc menu, hit Second Calc. Let's find that maximum value by using maximum. Once again, it's going to ask for a left boundary. We just want something slightly to the left of the maximum value we're looking for. Then it asks for a right boundary. Scroll over until the little blinking cursor or the little frog is to the right, and then press enter again for a guess. In this case, That 1.2655 e to the negative 6 times 10 to the negative 6 is actually the calculator's way of saying that's 0 and y is 4. So this value right here, 0, 4, is a local maximum value. For some reason my 4s sometimes look like 9s. Let's see if I can do a better job. 0, 4. How's that? And finally, let's look for this minimum value. Again, back to the calc menu. We're going to hit minimum, left boundary. We're looking for this minimum now. So let's say maybe right there, right boundary, scrolling over a little bit to the right of it, and press enter and then guess. And it's going to be 1.84-ish, 1.84, and then the y value negative 4.31, approximately. So boys and girls, that's how we use the full functionality of our calculator to graph and label the important points of a polynomial. You might be saying, Mrs. Darby, what about the solutions? You're exactly right. Let's go back to the calc menu and choose the 0 option to find out where it's crossing the x-axis. It looks like it's happening 2 places. Let me get a left boundary of this first 0 and a right boundary and get a guess. This first 0 is 1, 0. No big surprise there. I should have looked at my table of values, right? Then let's find the other 0. Again, we'll use the second option under the calc menu. We'll need a left boundary. We're looking for the second 0, so approximately, let's say here, maybe a little closer. All right, and then a right boundary. Again, notice the arrows that are designating the range because the calculator doesn't know which one you're talking about unless you give it a range. And so in this case, we have a 0, which is 2.38, comma, that looks like 0, obviously, since it's a 0. When you have negative 1e to the negative 12, tiny, tiny, tiny number. That's just another way of the calculator saying 0. So boys and girls, that's how we're going to use our graphing calculator start to finish to graph polynomial functions. It's kind of messy, I'm sorry about that, but hopefully you get the idea. Now let's leave graphing for a while and go back to add, subtract, and multiplying polynomials. To add or subtract polynomials, add or subtract the coefficients of like terms. And to multiply two polynomials, multiply each term of the first polynomial by each term of the second. Let's start with adding and subtracting. In this case, we've got this polynomial minus this one. It's a good idea, boys and girls, to rewrite that second polynomial distributing the negative. Why? To avoid careless errors. This is probably the #1 careless error that algebraists make, but not you, boys and girls. You're going to be careful and perform that distribution correctly. Nothing changed in the first polynomial, so let's just rewrite each of those terms. And now we're going to look for like terms. 2x cubed and a -1x cubed gives me x cubed. -5x squared and -6x squared is -11x squared. There are no like terms with the positive 3x, so we just write that down. And then -9 plus 11 is positive 2. There, we've subtracted two polynomials. Now let's multiply. That means distribute every term in this first polynomial by every term in the second one. And so basically it's just a lot of foiling that takes place. Remember, when you're multiplying terms, the exponents get added. So x times 3x squared is 3x cubed, x times -2x, -2x squared, x times 4 is 4x. That is the first round of distributions. Now let's take 3 and distribute. 3 times 3x squared is a positive 9x squared. 3 times -2x, -6x, and 3 times 4 is a positive 12. Now we look for like terms. There are no like terms with the 3x cubed, but -2x squared and 9x squared are like terms, giving us positive 7x squared. A 4x and a -6x is a -2x, and then plus 12. Now let's divide polynomials. There are two methods for dividing polynomials, polynomial long division and synthetic division, and we're going to do both processes. First, let's start with polynomial long division. This is going to be set up very similar to a long division problem with the divisor on the outside, x minus 2, and the dividend on the inside of the division symbol, x cubed plus 5x squared minus 7x plus 2. Now, you need to be careful when you set up your division problem and inspect the dividend prior. If there are any missing terms, you'll have to add placeholder terms to substitute for the missing terms. Here's what that means. This is a degree 3 polynomial. And since there's an x cubed term here, there has to be every subsequent term represented in the problem, an x squared term, an x term, and a constant. If any of those terms were missing, you'd have to add a placeholder. For example, if this 5x squared wasn't here, we would need x cubed plus 0x squared minus 7x plus 2. The placeholders keep your process neat and organized during the division. Now, let's start this way. Look at the first term of your divisor, the first term of your dividend, and ask yourself this question. What would I need to multiply x by to get x cubed? Of course, that's x squared. This x squared would need to be multiplied by your entire divisor and written underneath. So x squared times x is x cubed. X squared times negative 2, negative 2x squared. Now we have to subtract this polynomial from the dividend. However, many careless errors are made in this process, so let's distribute the subtraction and add instead. Here's what I mean. Draw the line, change the signs. By changing the signs, you've distributed a negative, and now you can add the terms and avoid some common careless errors. This becomes 7x squared. Bring down the next term, which is a negative 7x, and start the process again. First term, first term. What would you need to multiply x by to get 7x squared? Of course, a positive 7x. 7x times x is 7x squared. 7x times negative 2, negative 14x. Again, draw the line, change the signs. The x squared terms cancel. That leaves 7x. Bring down the last term, positive 2, and repeat the process one more time. What would I need to multiply x by to get a positive 7? X, and of course that's a positive 7. 7 times x is 7x. 7 times negative 2, negative 14. Draw the line, change the signs, the x terms cancel, and I have a remainder of 16. So this becomes 16 over x minus 2, and this is your entire quotient here. X squared plus 7x plus 7 plus 16 over x minus 2. Now let's use synthetic division with the same two polynomials. In this case, we take the factor x minus 2 and find the associated root or solution, which is 2. 2 goes into a little box off to the side, and then we just take the coefficients of the dividend and write them down. 1, 5, negative 7, and positive 2. Again, if there were any missing terms, we would need a 0 as a placeholder for the missing term. Here's how this works. Bring down the first number, multiply by the number in the box, and put that product under the second number. 2 times 1 is 2. Add those numbers, 7. Anytime a number drops below the line, you multiply it by the number in the box. And that's 2 times 7, which is 14. We add it to the negative 7, and we get 7 again. 2 times 7, 14 again. Add it to the 2, and we get 16. These four numbers represent our quotient. The rightmost number is the remainder. And then the constant, the x term, the x squared term. If there were any other terms, we'd keep going, x cubed, x to the fourth, etc. So our answer is 1x squared plus 7x plus 7, and then a positive 16 over the original divisor, which was x minus 2. Notice, of course, that that matches the answer that we got using long division. Synthetic division is a simpler, more elegant way to accomplish your division. Now let's review the factoring techniques that we'll need to factor polynomials. They're listed here in this box, starting with a general trinomial, which is taking a general trinomial and factoring it into two binomial factors. A perfect square trinomial, very similar. We have difference of squares, which is demonstrated here. Taking out a common monomial factor, also known as taking out a greatest common factor, GCF here. Sum or difference of cubes, these are two formulas you memorize if you have a sum of cubes or a difference of cubes. And then factoring by grouping, often used when you have 4 terms, and here's that process demonstrated here. Let's do a couple of examples, and remember that you always look for a common monomial factor first. When it says factor completely, the idea would be that maybe there are more than one type of factoring going on here. It could be take out a GCF and then do something else. But we always start with a GCF. And notice in this first example, we have one. We can take out a 3 and a y cubed. In doing so, that leaves y squared minus 16. Well, look at that. We now have difference of squares. So we continue factoring. This becomes y minus 4, y plus 4. Now, inspecting my answer, nothing can be factored further, so I'm done. Look at letter B, and there are 4 terms, which is my clue that I should probably use grouping, and there's definitely no GCF to start with. However, when your third term of 4 is negative, here's a little hint. Change this to plus a negative so that when you make your 2 groups, the negative goes inside with the third term. Group the first 2 terms together, the second 2 terms together. Let's find the GCF of this first group. We can take out a 4c squared. That leaves a c plus 2 inside. Here I can take out a 9 or a negative 9. I'm going to choose the negative 9 because when I do, that leaves a positive c plus 2 in parentheses, and we need these 2 things to match. If I had taken out the positive 9, I would have had negative c minus 2. Therefore, you make the decision so that these 2 parentheses match. Now that they do, we finish up by having c plus 2 as one of our factors and 4c squared minus 9 as the other. But wait, there's more. It looks like 4c squared plus 9 is difference of squares. So this will factor into 2c plus 3, 2c minus 3. And now, as I inspect my answer, it is factored completely. Then we go to letter C. I see a GCF right away. I can take out a 4x squared. This leaves 8x cubed minus 27. And since this is a perfect cube and this is a perfect cubed and a minus sign, this is difference of squares. This is the formula to factor difference of cubes. Here is the formula to factor difference of cubes. If you have a cubed minus b cubed, then it will factor into 2 parentheses, a little one with a minus b and a larger one with a squared plus ab plus b squared. So following this formula, the 4x of course is one of our factors. We can't lose that. In the small parentheses, we'll have 2x minus 3. In the larger parentheses, we have to square this first term. 2x quantity squared is 4x squared. Then ab is going to be plus 6x. And then of course b squared, since b is 3, that will be a positive 9. Now it's factored completely. All of these skills lead to the fundamental theorem of algebra, and it states this: if f of x is a polynomial of degree n, then the equation f of x equals 0 has at least one solution in the complex numbers. In general, a polynomial of degree n will have n solutions, provided any repeated solutions are accounted for. Here's what this is saying. We've gotten to the place where we realize whatever degree of the polynomial, that will be the number of solutions to that polynomial, taking into account repeated solutions, imaginary solutions, irrational solutions, whatever they may be, there will be that number of solutions. A degree 5 polynomial, 5 solutions. Degree 7 polynomial, 7 solutions. And we're at the place where we have all of the skills necessary to find all the solutions of a polynomial. How do we find these solutions? Using all of the skills we've learned along the way: synthetic division, factoring, using the quadratic formula and the rational root theorem. Well, let's discuss the rational root theorem briefly before we embark upon finding solutions to a polynomial. Given a polynomial with integer coefficients and with q representing factors of the leading coefficient and p representing factors of the constant, then every rational zero will have the following form: p over q, where p represents a factor of the constant term and q represents a factor of the leading coefficient. Here's a little example. Let's say you have something like y equals, say, 2x to the 5th and then blah, blah, blah. Let's say minus 3 as your constant. P is 3 and Q is 2. You would list all the factors of P, which in this case are 1 and 3, that's all. List all the factors of Q, 1 and 2. Then the only rational zeros of this polynomial would have to be of the form P over Q. So the P over Q list for this polynomial would be 1 over 1, 1 over 2, plus or minus always, 1 over 1, 1 over 2, and then 3 over 1, 3 over 2. Pause plus or minus 3 and plus or minus 3/2. Now that's significant because it narrows down out of the infinity of numbers that we could be looking at the only possible rational solutions to the polynomial. It's a great starting place when you're finding solutions. In our final example, we're going to find all the zeros of the polynomial function. We start with the fact that it's a 4th degree polynomial, so we know we're looking for 4 solutions. That's what the fundamental theorem of algebra tells us. However, what are the solutions and where do we start? Well, we start with the rational zero theorem. Remember that 6 is P and Q is 2. The list of factors of 6 plus or minus 1, 2, 3, and 6. The factors of Q plus or minus 1 and 2. Therefore, our P over Q list for this polynomial, 1 over 1, 1 over 2, so plus or minus 1 and 1/2. 2 over 1 and 2 over 2, so plus or minus 2, but 2 over 2 is 1, I don't need to list that again. 3 over 1, 3 over 2, so plus or minus 3, plus or minus 3/2. And finally 6 over 1 and 6 over 2, plus or minus 6, but since 6 over 2 is 3, I don't need to list it again. 1, 2, 3, 4, 5, 6 times 2, 12 possible rational zeros. If this polynomial has any rational zeros, they must be on this list, which is great because we can use this list to start looking for rational solutions. I'm going to use a synthetic division chart with the original polynomial. The coefficients are 2, -3, 4, -9, and -6. Now, the full synthetic division process takes up too much space. So we're going to just use an abbreviated chart so we can find out if any of these potential zeros are actual zeros. Let's start with 1. Bring down the 2. 1 times 2. Instead of writing 2 down, we simply mentally add it to -3 and get -1. 1 times -1, -1 plus 4, 3. 1 times 3, 3 plus -9, -6. So close, but not quite. So this one did not work. Let's try -1. Bring down the 2. -1 times 2, -2 and -3 is -5. -1 times -5, 9. -9 and -9, -18. This one's not going to work either. Let's try 2. Bring down the 2. 2 times 2 is 4 and -3 is 1. 2 times 1 and 4 is 6. 2 times 6 is 12 and -9 is 3. 2 times 3 is 6 and -6, 0. This is how we know that we have a winner. 2 is an actual zero. Now, we don't continue on with the full polynomial. We take what's called the depressed polynomial and continue the process of looking for solutions. Set up another synthetic substitution chart with these coefficients, 2, 1, 6, 3. Notice that P is 3 now, Q is 2, so that eliminates 6 as being a possibility. We've already tried 1 and 2. Let's look at -2. Bring down your 2, -4 and 1, -3. That's a positive 6 and 6 is 12, and then -24, not working. Let's go back to 1/2. Bring down the 2. 1/2 times 2 is 1. 1 and 1 is 2. And then 1/2 times 2 is 1, and 6 is 7. I can see this is not working either. Let's look at -1/2. Bring down the 2. -1/2 times 2 is -1 plus 1 is 0. -1/2 times 0 plus 6 is 6. And -1/2 times 6 is -3 plus 3 is 0. Great. So far then, we know that 2 and -1/2 are actual zeros. Once we get down to a depressed polynomial that is a quadratic, we don't continue with this trial and error process. We take the quadratic, 2x squared plus 6, set it equal to 0. We could factor, use the quadratic formula, whatever quadratic method we want to solve this quadratic. We have so many, completing the square, etc. But in this case, the easiest way to solve this is simply to subtract the 6 over and divide by 2. Taking the square root of both sides reveals that our final two solutions are going to be imaginary. So the complete list of solutions, 2, -1/2, and plus or minus I square root of 3. And that's the fundamental theorem of algebra in action. That's it for today's lecture, boys and girls, and I leave you with Math World problems. God bless you, boys and girls.